theoretically a short circuit for the capacitor, but is it really? Answer is practically it will be if you follow this criteria here. Criteria is this. If you have a capacitor and a resistor and you want to short circuit the resistor, like short it out at certain frequency, at certain minimum frequency. At higher than that minimum, it will be definitely true. For example, if I make this a resistor, this is a resistor value, say 100 ohm. If I make that reactance to be minus 10J at 100 hertz, the minus 10J will dominate over the R. It will be like a short circuit. It will be much, much less than 10 ohm. That is considered like a shorting out the resistance. Now, if the frequency goes over that 100 ohm, and I keep my capacitor to the same size, obviously, if it was minus 10J, it will go even smaller, like minus J maybe, or minus 0.1 of a J. Minus J or minus 0.1 of a J is much, much smaller than the size of that resistance. So it will be like dead short. Next thing is impedance between 2 poles. It's called series impedance between 2 poles. How do I make the capacitor act like a short circuit compared to R? All right, same criteria. If at your minimum frequency, your reactance is much, much less than R, then the impedance between X and X, Z series, will be nearly equal to R. So I can put something like approximation in here, you know, like approximately equal to R, to be approximately equal to R. Condition for that is at the minimum anticipated frequency in the application, if you choose your capacitor based on that minimum frequency to be a tenth of the R, for over that frequency in the application for frequencies over that minimum anticipated one, then this will be even more accurate. Impedance will be equal to R. I can put an example in here if you want to convince you. Here, don't write it, just pay attention because you're supposed to know this. Suppose you have an AC source and there is a capacitor with a minus 10J, and there is a resistance which is 100 ohm. And this is the VO and this is the VI. All right? I want to see VO and the VI, the transfer function VO over VI. What will be that value? Okay, VO over VI will be equal to output phasor over input phasor, magnitude, output peak over input peak, or RMS over RMS, doesn't matter, will be equal to, here, 100 divided by 100 minus NJ. That is 100 over square root of 100 squared, square root plus 10 squared, and the angle will be tan to the minus 1 of 10 over 100. So this will be equal to, let me get my calculator. We are trying to figure percentage of error. That's why. I need a calculator. Here. This is the calculator. So 100 squared plus 10 squared equals square root. This will be 100.5 denominator, 100.5. The top is, of course, 100, so the magnitude will be 100 over 100.5. 100 divided by 100.5 is equal to 0.995. And the angle will be some inverse of 0.1. 0.1, we go inverse tan equal about 5 degrees, 6 degrees, 6 degrees. Okay, what does that number, complex number, tells us? The complex number tells us VO is 0.995 of the VI. See? Output voltage here to the ground is 99.5% of the input. Doesn't that mean almost like 100%, 99.5? Only it's 0.5% in error. So that means if you assume this is a short, because it is 10 times smaller than that, automatically with the short you could tell this ahead of the time, instead of doing all that calculation. You could say, hey, if this is short, voltage here is the same as that. That's why we are assuming in here, voltage at this end, which feeds the circuit, amplifier circuit, voltage at the other end, which is the towards the circuit, they're the same. Because this part is the R, and that is the C. Agreed? Only one time we go over this. So that will be our criterion. If it is 10 times smaller at a minimum frequency of concern, then over that frequency it will be much, much smaller, and then you will be as accurate as 99.5%. So that's nearly 100%. Rather than, if you want to make this capacitor act like a short at a frequency, guess what should be the size of the capacitor? Infinity, in order to make that happen. It's infinity capacitor, big capacitor, unlimited, doesn't exist. And again, what will be the drawback of having a large capacitor? Oversize. So if you make this capacitor unnecessarily too high, over here, in the circuit, when you turn on the power supply from 0, all these capacitors would be flat initially. The circuit is dead, flat, doesn't store energy. So when you switch and the circuit tries to reach its steady state quiescent DC values, the final DC state, it will take forever to get there if your capacitor is oversized. So you're not free to choose big capacitor there unnecessarily. No, you don't do that. You just ask what is the frequency that you're dealing with, the least of that, and that's your F minimum. 100 hertz, okay, you want to amplify 100 hertz voice and up? Sure, so your 100 hertz is your minimum. Then you take care of that 100 hertz, determine capacitor based on the 100 hertz for all frequencies over that, going to 20, 30 kilohertz. Oh, that accuracy will be way better than 99.5%. It will go towards the 100%. But you never reach 100% unless you have infinite capacity. That's it for all. I will not repeat this again, okay? So from now on, we are using that criterion for the analysis. So here comes the way to determine that. In order to determine the capacitance in here, there, we need to see what kind of impedance it sees this way and what kind of an impedance it sees in the other direction. Okay? So if you short circuit that power voltage source, then you will see that impedance that way with respect to ground, impedance seen this way, which is RS, with respect to ground. Through the ground, they will form two series resistors going parallel with that capacitor. Two series resistors going in parallel with the capacitor. Situation is like this. See, take that, put a resistance there, RS, and this is the ground. And then, here, ground. And then put a resistance there with respect to ground, call it Rin or Ri. Then remove the ground, connect. Now you see the two are in series going parallel with the C. All right? So I have to make that capacitor 10 times smaller, its reactance 10 times smaller compared with those two being in series. That's it. That's it. So you've got to determine input impedance and then output impedance viewed in that direction towards this source. So we go to the original circuit. The input impedance, which is VI divided by II to the right, would be R1 parallel R2 parallel RI. Here you are. RI, R1, R2 parallel to RI. Input impedance looking to the left will be RS. So we go to the next page here. we compose our circuit based on that concept. X sub C1 is there. On one side it sees RS, input resistance of stage, amplifier stage. To the left, it looks to the source resistance of Vs. So X sub C has to be much, much less than Rs plus Ri because the two are in series. Then this, so a tenth of it is considered much, much less. Then you substitute for X sub C at F minimum, its reactance, and then you balance it against the R 1/10 of the Rs plus Ri, you get this equation. 10 over 2 pi F min times the resistance. In this composition, it is the two are series, so put it there. Next, the output resistance. So I will go back to the previous page, which is here. And right there. Okay. So we are concentrating on C2, that edge, which is the output to the load coupling capacitor, C2. All right, when we look from to the right, we see the load resistance, RL. When we look to the left, we see the resistance, these two parallel together. RO of the transistor, RC of the, RO internal of the transistor, RC the collector resistance. So again, RL goes in series with the parallel combination of RO and RC. See how they are forming. This is parallel with that one because it terminates to the ground. So you will see RL in series with RO parallel RC. Here comes the equation. So we go to this one. There you are. Okay. So I drew partial output side of the amplifier. Can be regarded an independent voltage current source. Excuse me. So RL appears to be series with the parallel of RC. This is parallel RC or RCRO, which I said, just to cut this short, I never put RO in my exam, hardly, unless I intend to do that. It's just a RC series with RL. Because if this is infinity, the whole outcome is RC. So X of C2 has to be a tenth of RL plus RC. So you go here, we build another formula. Here we build another formula. The formula is here, 10 over 2 pi F main, RL plus RC. Okay. These are the easy parts and obvious parts. It's the last one which will be questionable here. There. This one has an argument there, but I need to explain that. Now we are trying to determine the CE, the capacitor that connects emitter goes parallel with the RE to the ground. So if I go to the original circuit, I am focused in here. Sorry, second. I'm focused there. Okay, it's this guy here. This capacitor looks into the circuit from that node towards the circuit. Always, without exception, students, when they're beginners, excuse me, they think because CB is connected to RE in this fashion, the parallel resistance is RE. Doesn't that look that way? This capacitor CB is parallel to RE, but actually, no. There's a lot more going on. Behind that, there is something else. Behind that, there is an active circuit. And we need to calculate the input impedance to the circuit from a weird angle. and that angle is through the emitter. So we are going to look back through the emitter towards the circuit and see what is really the output impedance of that circuit with active transistor at the emitter. We know that whatever it is has got to go in parallel with the RE. So we have got something to the left of the emitter towards the circuit, excluding RE and the CB. So that resistor will go parallel with RE, then the combination will go parallel with CB. Now, the news is that output impedance from the emitter is awfully small. Very, very small. It goes into the few ohms, 5, 6 ohms to maybe 20 ohms. So it is so small that you will need quite a big capacitor to be even smaller than that at that frequency. For example, 5 ohm. If that is really 5 ohm, the total that I'm looking away from the CB, if it is 5 ohm, then imagine the capacitor CB has to be 0.5 of an ohm at that frequency. Compared to other resistors, RS is 1K, input impedance is 2K, RL is 5K. You see, these are very large, so it makes the capacitors C1 and the C2 pretty small. It's easy to make them short because their accompanying resistors are pretty large. But this guy is the one, CB, which its accompanying resistor viewed in that angle is awfully small, in the order of ohms. So the CB has to be even shorter than 5 ohm, which renders it big when you calculate at the F minimum. Indeed, in amplifiers, without exception, this is what you will see as typical values. C1, 1 to 10 microfarad. C2, 1 to 10 microfarad. CE, 1200 microfarad. You see? 10, 10, 1200. Or 3300 microfarad for the CE. It's a big capacitor. Why? What makes it happen? Is it RE? No. There is more than RE that goes in parallel. So what I'm going to do in here to show you the proof that why it is so small. Okay, here comes the proof. So we go to that last page. Okay, so this is the model for the circuit. In order to calculate what is the input impedance viewed towards the emitter, we partition CB to make it external, partition RE, bring it out. It will make analysis simpler if we exclude them initially. Then put a test voltage here between E and the ground in the AC model. Calculate the test current flowing into the circuit. Okay? And then determine what is the output impedance viewed at the emitter. In order to do that, you will short circuit this source, and then you calculate the response of the circuit, VT over IT ratio, and that will be your output impedance. Okay, so separate RE from circuit, short circuit VS, apply a test voltage VT, and determine the subsequent test current flowing into. Our out will be ratio of your test voltage to the test current. 5. Then X of CB in here, reactance of that capacitor has to be much smaller than parallel combination of this resistor with what you see between E and the ground. We call that R out, lowercase r out. This is the one as the ratio of VT over IT. So remember, R out is the impedance seen straight at the emitter, excluding RE and CB. So we are trying to calculate that one. Then once you determine this total impedance, R out parallel with the RE, you make that 10 times smaller, and you will have this equation to determine CB. CB has to be 10 times 2 pi f minimum. I put it R star out. What is the difference between R star? R star out is the combination of RE parallel with the resistance seen from emitter with respect to ground, which is called R out. This kind, R out. Remember, R out is VT over IT. VT over IT is excluding RE. So how do we proceed about that calculation? From the diagram that you see over there, it's a voltage divider rule. VBE can be calculated in response to VT. VBE, what's VBE? VBE is equal to R pi divided by this resistance, all three resistors in series, plus R pi. It's R pi over that in parallel, plus R pi. Here. R pi divided by RS, R1, R2, which is combination of this whole resistors, all four of them. Where is it? RS, R1, R2, and R pi. So we do that, total resistance, and then VBE is equal to that ratio multiplied by VT. With a negative sign because the sign is reversed in here. See, that's a positive, negative. This is positive, negative. So VBE is negative of the VT. We've got to account for that negative sign. So this is the voltage across the R pi due to voltage of VT. Equation 1. Then you write the KCL at E. Again, all of this is excluding capacitor resistance. KCL at that point is equal to IT as current flowing towards the E, GM VBE, GM times VB as the current flowing from that current source towards the node, and the current that flows in this branch, which is IT VB over R pi, the current flowing in is VBE divided by R pi. Essentially, this is IB. So sum of all these currents must add up to 0. In other words, current this way, current that way, current this way, coming through here, they should add up to 0. Equation 2. Between 1 and the 2, you eliminate VBE, get rid of VBE. So you take from here, substitute here, and this will be the outcome. VT over IT ratio, which is known as R out, will be RS parallel R1 parallel R2 parallel R pi divided by 1 plus GM R pi. This will be the total output resistance viewed at the emitter of resistors. Okay, I can give you a simplified circuit and do the same thing just to convince you. Here, R pi, there is a source in here going to a resistor there, RC and then RL. I'll show you an alternative method, which often is even easier. Say you have a source resistance in here, Rx, which, and the source over there. I'll tell you what is Rx. Rx is the resistance, break it down. Rx is the resistance viewed in this plane, to the left of this hand. Look at the left of that hand, over here. You see RS parallel R1 parallel R2. We can present all of it with an Rx, just to simplify it, because I'm showing you a really easy method. That is your B, this is your E, and this is your VB. And that is the current GM times VB. Okay? This is some kind of a source. VGTH, Thevenized source resistance. Don't worry about it because you're going to short circuit. There is an alternative way to calculate R out. R out is equal to open circuit voltage, voltage divided by short circuit current. Open circuit voltage between emitter and the ground. Short circuit current between emitter and the ground. Let's see if it will come out exactly to the formula that I have posted, a little lower than that. This is an easier method. First, open circuit voltage, EOC, known as EOC. EOC. This is ISC, short circuit. EOC is equal to, what is the voltage from here to here? If you are going to put a voltage in there, VGTH, if it is open, then the current in here is equal to 0. There is no current in this branch. Here, there's no current in here. That current is IB times 1 plus beta. Because remember, the current in the emitter is always IB plus IC. So IB, beta is the IC, IB times 1 is the IB. That quantity is equal to 0. If this quantity is equal to 0, what does that tell you? IB must be 0, isn't that right? There's no current here, no current here either. If there is no current in this branch, there's no voltage drop in that branch. If there is no current there, there is no current in here. So if you have a source in here, VGTH, you have that voltage in here, VGTH. So here it is, VGTH. That will be the open circuit voltage there. Half of the problem is solved. The second one is, what is the short circuit current? Check here. Now we change the situation into a short. You have no more voltage in here. It's a 0 because you shorted, right? Now we need to calculate the short circuit current flowing through that short circuit. If I get IB in here, under the short circuit, problem is solved. Because if I get IB, this branch is going to be beta times that one. In other words, 1 plus beta times IB. So I'm going to calculate that. Very easy, see? It's a 0 volt here. You have VGTH over here. You have an Rx and R pi. So I of B simply is VGTH divided by Rx plus R pi. Okay, this is IB. Then what is IE? IE is 1 plus beta times IB, because they combine into 1. That short takes current from this side and also from that generator here. Okay, so your I short circuit, which is the I short circuit, ISC. So your I short circuit here, I short circuit, is going to be VGTH over Rx plus R pi, here, R pi, multiplied by 1 plus beta. 1 plus beta. Here's IB, this is 1 plus beta, and that chunk is IB. This is the IB from here. Now, final thing, get the ratio, and you will get the answer. What is R out? You have open circuit voltage between the two nodes. You have the short circuit current between the two nodes in terms of this generator, but the ratio, when you divide the ratio, see, this VGTH will cancel that VGTH, and you will end up with only resistors. So let me finalize the answer here. R out, therefore, from here you have VGTH due to that, divided by I short circuit is VGTH 1 plus beta divided by R, big R, Rx plus R pi, which adds up to, VGTH cancels from top and bottom, to R out, I'll write it here, equal to Rx plus R pi divided by 1 plus beta. 1 plus beta, okay? So, now we're going to make some assumptions which will really simplify the answer. So let me just go there and check my diagram here. Here, this answer here. So we are going to arrive here. Check it. We are there. Here is your 1 plus beta. Here is your R pi. Rx is the resistance viewed to the left, which remember what we had in the left. We had Rs, we had R1, we had R2, that was power supply, and this is, we were looking in that direction, a short circuit over there. So you see that all the three resistors, Rs, R1, R2, are going to be in parallel, and is represented with a simplified Rx. So that's it. So this Rx that you have over there is R1 parallel R2 parallel with the Rs. Maybe this method, you like it better because it's easier. Short open circuit voltage divided by short circuit current. Powerful method. You know, there are two methods to determine output resistance or input resistance. Either way, it's the same. Input or output resistance, there are two methods. No. One is the test voltage, test current. Second one is open circuit voltage to the short circuit current, period. There is no other method that I know exists. Which one can use? It depends on the circuit. Sometimes OC over ISC works easier, maybe here, rather than the other one, V-test over I-test. Anyway, I did it by V-test over I-test method over here, and this one that I did on the board is by open circuit voltage to short circuit current. They lead to the same answer. Okay, so this is what you need to bear in mind. You have an amplifier and you want to determine the CE of that amplifier. Of course, you need to figure out R pi. You need to know what's the beta. And then you need to know what is your network that you have, R1 and R2, and what is the source resistance that you have coming from preceding stage, from the signal generator, that end. You need to know that, work out the total of that as a parallel combination, add R pi, divide by beta. However, one point, What if the source didn't have an RS? So pay attention here, because my students, of course, if you don't know the roots, you'll make such a mistake. What if RS is non-existent, short? So what would you assume for RS? A 0 or infinity? Which one? Here. I'm going to the original circuit, the earlier one. Let's say this one. Oh, no, second one. Sorry. This one. Okay. What about if this RS was non-existent? A generator was straight fitting that end of the capacitor. What would be then, how would I modify the output impedance viewed at the emitter? This is what you should do. So remember, if this doesn't exist, RS is short, is 0. You should go to that last line here, and substitute 0 in parallel with R1 and R2. Now you tell me, what is a short circuit parallel with R1 and R2? Wouldn't that be a short circuit? Yeah. Still a 0? So that's it. Take this out of the equation. Wipe it out. If you didn't have a capacitor, it doesn't require thinking. If RS doesn't exist, it's short. It's easy. R pi divided by 1 plus beta. Now, notice that if this could be eliminated, your output impedance R out at the emitter would be R pi over 1 plus beta. R pi over 1 plus beta, if you notice, is approximately the GM. See, R pi? Because that's how we calculated R pi. R pi was equal to beta over GM. Okay? So GM is equal to beta over R pi, so reciprocal of that. So if you didn't have the RS, it would be R pi over GM, R pi over 1 plus beta, or R pi over beta, approximately equal to 1 upon GM. So here is the rule of thumb. R out is approximately equal to 1 upon GM if RS turns to be 0. Non-exist. 1 upon GM. And this 1 upon GM happens to be a very small quantity, because the GMs are in the order of 0.5 Siemens. GM goes from 0.5 to 0.05. 1 over 0.5 is 2 ohms, as low as 2 ohms. 1 over 0.05 is like 20 ohm. So that capacitor I was talking about, CB, has to be shorter than the 2 ohm. That means 0.2 of an ohm. So you need a pretty big capacitor to do that. Actually, with common emitter amplifier, that's the bulkiest part, that capacitor. And also expensive. It's more expensive. Okay, so this was the most difficult part of determining. But I tell you what, these two equations are absolutely vital. From now on, no matter which combination we are using, common collector, common emitter, that thing is going to show up constantly. Impedance viewed at the emitter of the transistor, there, and E towards the transistor is R out. Now, how do you determine then the total, the CB? It's easy. Now, when the capacitor looks back in the direction of that arrow, it sees R out, that R out, not the star, R out, parallel with the RE, which usually RE is so bigger than the R out that the R out dominates. So roughly speaking, you look back, the capacitor has to have an impedance much less than 1 over Gm. Very good approximation rule. Much less than 1 upon Gm. 10 times smaller than 1 upon Gm. Because as I said, REs are usually much bigger than 1 upon GMs. REs are like 2 kilo ohm, and the 1 upon GM is 2 ohm. 2K parallel to 2 ohms is just 2 ohm. When we do problem, you will get the feel of it, how it works. So that's about it. Complete. And we can therefore model here. We can model 3200. We can model our amplifier, combinator amplifier, with the following. CE AC model equivalent circuit. So this will be your amplifier, RI, which will be R1 parallel R2 parallel with R pi. Then there will be a voltage source if we try to present it with a dependent voltage source. This will be the collector node. That will be RC, which is the R out of the amplifier at collector RC, doing that way. That is a voltage source given by minus GM times VI times RC times VI, which this quantity is called AV, no load. That means external to RL, means i.e. external to RL. See, RL doesn't show in here, it's RC, put it C clearly. And then this will be the VI input, and this will be the VO output. That's your model. GM is equal to IC quiescent over VT. This will be our tool for calculating equivalent model for the amplifier. But where is the other? VS, VG. Okay, here is VG. V of the G, or source, you can call it. Here is the RS, source voltage. Let me call that source. I think I referred it as source, so don't mix them here. V of source, RS, which is external to the circuit. The coupling was capacitor there, which has been considered short. On the load side, this is what you have, RL. That's where it couples into this load, RL. And once load is connected to that point, this becomes the VO under the RL. So bear in mind. What is the output voltage without the load resistance? Go compute the voltage here, which is minus GM RC VI. Fine. What happens if you add a resistor? You don't have to recompute that. Simply draw this model, which is solid for the amplifier, add a resistor there, and progressively calculate the voltage from node to node transfer. Here's how to do that. Say you have 50 millivolt over there. This is given, that's given, you calculated that, right? What's the voltage at the VI? you can calculate voltage divider. Do you see that? Simple voltage divider. Once you get the VI, transfer it here. Then you determine what's the voltage coming off of here. Internal voltage. It's a dependent source. See, VI multiplied by the voltage gain AV is a dependent source. So you get the voltage here. Once you get the voltage here, if you don't have RL, that's your output voltage. But if you have RL, write a second voltage divider. Did you get it? And you get the voltage at the VO under the RL, under the influence of RL. So quickly, I'll put a problem on the board, and I think we should be able to solve it pretty quickly. Then I've got to get rid of all of that. So I have room to work on the board. Here. Don't need anything there. Let me